Hello and welcome to Textbook Engineering Problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 4.36. Okay, so this problem says, in the production of a bean oil, beans containing 13 weight percent oil and 87% solids are ground and fed to a stirred tank, the extractor, along with a recycled stream of liquid N-hexane. The feeding ratio is 3 kilograms hexane per kilogram beans. The ground beans are suspended in the liquid, and essentially all of the oil in the beans is extracted into the hexane. The extractor effluent passes to a filter. The filter cake contains 75 weight percent bean solids and the balance bean oil and hexane. The latter two are in the same ratio in which they emerge from the extractor. The filter cake is discarded and the liquid filtrate is fed to a heated evaporator in which the hexane is vaporized and the oil remains as a liquid. The oil is stored in drums and shipped. The hexane vapor is subsequently cooled and condensed, and the liquid hexane condensate is recycled to the extractor. And then they give a picture, basically this picture that I've drawn here, but with less information. And then part A, they say, draw and label a flow chart of the process, do a degree of freedom analysis, and write in an efficient order the equations you would solve to determine all unknown stream variables, circling the variables for which you would solve. Okay, so I don't think I actually did the degree of freedom now that I'm reading it again, but I'll leave that one up to you guys. They have a good section in the book about how to do a full degree of freedom analysis, and I've done several on a bunch of these other problems, so I'll let you guys do that part unless you have specific questions on how to do degree of freedom analysis. But I've drawn out the process here. You can see I've added some of the information they had in the problem statement about weight percents going in. They give us this ratio here. And then they say that this ratio is the same as this ratio. Okay, and yeah, okay. Oh, one thing that they don't have on their diagram that you really do need to pay attention to is they say, okay, I have a certain amount of hexane being recycled here, right? But I also have a certain amount of hexane leaving the filter cake, right? Okay, so if you don't have a certain amount of hexane makeup here, then you're eventually going to run out of hexane. Okay, so when you do an overall balance on the process here, so you say I take all the inputs and all the outputs. If you don't put this in, then you will run into problems. Okay, so I don't know if that's part of the reason why some of you guys might have run into problems on this, is because you didn't account for the hexane makeup. They kind of reference it in one part of this problem. I'll point it out when we get there. But they don't put it on their diagram. Okay, so it might have thrown you off. That there has to be an input of hexane. You're not perfectly recycling it, and you're bleeding off some of it here. Okay, so you do have to have a hexane input. Okay. All right, let's do the overall mass balance. We have M1 going in, that's the beans. And then you have a certain amount of hexane going in, which is equal to the hexane that's going out in line 3, right? Okay, so we're adding in the same amount that we're losing. And then M3, all of M3's mass is leaving, and all of M6's mass is leaving. Okay, that's the oil production. Okay, so those are the two inputs and the two outputs. Okay. Then we do some substitutions, cancel some of these things out. The hexane going in and the hexane going out cancel each other out, okay? And then we're left with this equation. I wrote a one, circle of one right there because that's an equation that we end up using later on. We can't do anything else with it right now because we have a couple of unknowns here that we can solve for later. I divided everything by M1 because later on they're saying, they say calculate the yield per the feed, right? Okay, so per the feed means divide by M1. Okay, so all we have to do is solve for M6 divided by M1 or M3 divided by M1. Or, everything's in terms of N1, okay? Okay, so now let's switch over to doing a balance around the extractor so that we can figure out some of our other mole fractions. So we know these mole fractions going in. We want to calculate what the mole fractions are coming out, okay? So all of our sub 2 mole fractions, okay? So let's do our balance. Going into the reactor, we have this much bean oil going in, and we have this much going out. This much solid going in, this much solid going out. We know that we have a certain amount of hexane going in M5, and total amount of mass going in. This is an overall mass balance. We have a certain amount of hexane going into the reactor, certain amount of solids going in, and that's going to equal how much hexane and solids and wherever going out. Okay. We do also know they gave us this ratio that M5 divided by M1 is equal to 3. Okay, so if I divide everything by M1, I don't divide everything by M1 here, but we're going to end up doing that anyway. So we end up with that M2 divided by M1 is equal to 4. Okay. Okay, so in that case, then we can solve all of these, right? Because we know what the weight fraction of oil is in stream 1. Now we know what the ratio of M1 to M2 is. Now we can calculate what the weight fraction is here. Okay, so that's what we do over here. Calculate our weight fractions. And then the last weight fraction we can just calculate using our process spec. 1 minus the other 2 weight fractions equals this weight fraction. Okay, so when I highlight it green, that means it's check, we solved for those. Okay, so we know what those 3 variables are. We know what all the weight fractions are for stream 2. Okay, now let's start writing our few other equations here. We can do, we were given that the ratio that hexane and oil were in coming out of stream 2 are the same ratio as they are leaving here. Okay, so that's what this information is. Okay, so those ratios are equal to each other. So that means that this relationship is true. And then we also know that the oil, the process variable spec, right? So we know that the oil plus the hexane is equal to 1 minus the total amount of solids, and they gave us the solids, so we know that. So now we have 2 equations, 2 unknowns. You can solve them substitution or whatever you want. And now we know what all of the weight fractions are in stream 3. Okay. Now, instead of doing a balance around stream 4, around here to do stream 4, I thought since we know what M6 is, it would be easier to just do the entire balance around the entire process again. But instead of doing the overall balance around all the masses, we're going to do the overall balance for just the oil. Okay, so oil going in minus oil going out in the filter and minus the oil going out in production. Okay, and we divide everything by M1, and we get this relationship. And if you remember, I pulled stream 1, or our equation 1 that we already solved for. That's the full mass balance there. So we have the oil overall mass balance, and then we have the overall mass balance for everything. This is the oil overall mass balance, okay? So we have two equations, two unknowns. What are our two unknowns? These are our two unknowns, okay? So two equations, two unknowns. Now we can solve for those. Substitution, using linear algebra, whatever. So now those are good to go. We know those. Okay. Now I did not solve for stream 4, but we don't really need all of these to solve the rest of the problem. So I just didn't solve for those ones. But it should be pretty easy if you know all the rest of these variables, you can solve for stream 4. It shouldn't be too much harder, especially if you know. So we know M3 with respect to M1 and M2 with respect to M1, and we know all of the weight percents. Just do a balance around the filter, and you can figure out what M4 is. If you have to figure out what M4 is, that's how you would do it, okay? Okay, let's go to part B. Calculate the yield of bean oil product. Kilograms of oil per kilogram beans fed. The required fresh hexane feed. Here, that's the part I was talking about. The required fresh hexane feed. Hint, hint, there's another feed here. They don't put it on their diagram for some reason, but they know that it belongs there, right? The required fresh hexane feed, okay? In kilograms of hexane per kilograms of beans fed, and the recycle to fresh feed ratio in kilograms of hexane recycled per kilograms of fresh feed, okay? I don't think I calculated that last one, but we can do it real quick. Okay, so how much oil did we produce per how much we fed? That's M6 over M1. Okay, so basically I took all of these equations that we solved, right? We figured out all these greens, right? And calculated all of the properties here, right? Okay, so now we have all of our properties in front of us. The one that they asked us, the ratio of how much oil is produced per how much mass we fed, that's this one right here. The ratio of fresh hexane feed, that's this one right here. So we have M3 divided by M1, that's the total amount of hexane that's leaving times the total weight percent. That's the total. All this together is the total amount of hexane leaving is also equal to how much you need to add, the fresh feed, okay? So this ratio is this right here, okay? And then the last one, the recycle to fresh. Okay, so the recycle to fresh would be this value divided by this value, okay, or vice versa. So it would be 3 divided by this number, okay? So that would be M5 over M3, basically. M3 times WH3, right? Okay. So 3 divided by that, you just pull up your calculator. 3 divided by 0.278. That's 10.8. Okay. There you go. That's the last thing that they asked about. Okay. Part C. It has been suggested that a heat exchanger might be added to the process. The process unit would consist of a bundle of parallel metal tubes contained in an outer shell. The liquid filtrate would pass from the filter through the inside of the tubes and then go on to the evaporator. The hot hexane vapor on its way to the evaporator on its way from the evaporator to the extractor would flow through the shell, passing over the outside of the tubes and heating the filtrate. They basically just explained a shell and tube heat exchanger. Okay. How might the inclusion of this unit lead to a reduction in the operating cost of the process? Okay, so how does this lower your costs by adding a heat exchanger? Well, it doesn't at first, right? Because you're paying the capital cost of a heat exchanger. So you would need to make sure that the amount of money you're saving by getting the heat exchanger eventually pays for the heat exchanger and then ends up saving you money, right? Okay, but that being said, if you assume those things are true, how would it save you costs? Well, it reduces your costs by lowering the demand on the condenser, right? It takes power to use a condenser. And so you're putting in energy to cool off that hexane so that it becomes a liquid, right? Well, instead of using all that energy, you could cool it off. You could cool off the stuff before it gets to the condenser, take some of that energy out, and put it back into the evaporator, right? Because the evaporator needs a lot of energy in order to boil off all that hexane, turn it into a gas, okay? So basically, you're taking some of the energy that would need to be taken out in the condenser anyway, and just keeping it in the evaporator, okay, by preheating the stream that goes into the evaporator. And then the stream that's hot that would go to the condenser, it doesn't have as much energy, so you don't have to pull as much energy out with the condenser, okay? So it lowers costs on the demand on the condenser, and it lowers the demand to heat the evaporator because you're just keeping more of that energy in the evaporator, basically, okay? It's like insulating the lines, kind of. Okay. Part D. Suggest additional steps that might improve the process economics. Okay, so I thought of a couple of things, and then even now just reading through this problem again, there's one other thing that I'll talk about, okay? So the first thing is that you could centrifuge the filter cake. There's quite a bit of oil and hexane that's leaving in the filter cake, right? So that doesn't seem very optimal. There should be a way to get more solids removed from the hexane and oil, right? So getting a better separation there, I don't know what the filter cake looks like or how that would work. I thought of a centrifuge. Basically, you spin it really fast, and it separates the material by density. So if the solids, which are typically more dense than the liquids, you spin it really fast, and the solids will move away from the center of the centrifuge, and the liquids will move toward the center of the centrifuge, or the lighter material, the less dense material, which would probably be like the oil and the hexane, would move toward the center. And so then you can pull the liquids from the center of the centrifuge, and then you can scrape out the solids kind of at the back end, okay? But solids handling is pretty tough, so they may or may not work. Another thing that you could do is improve the feedstock. So the amount of oil that's in these beans is only 13%. That's like pretty low. Maybe that I'm not very familiar with the bean oil content, right? I'm not a connoisseur of that sort of thing, but we've got only 13% oil inside of these beans. Well, what if you found a new farm that produced beans with like 20% oil? Well, then you would be getting more oil out of the beans, right? And then you'd improve your yield, right? Okay. So that's another thing you could do, is find better quality feed. And then the last thing I thought of is they're storing. It said that the oil is stored in drums and then shipped. You might be able to, so storing product is usually a bad idea. You don't want to keep inventory on the ground where you're working. You don't want to like store that on site. You want to produce as much as you're going to ship and that people are going to buy, right? That in an ideal, perfect world, you would never have to store any of your product, right? Okay, so if there's a way to prevent having to pay storage on the product and to just maybe as the oil is produced, you put it inside of like a truck or something like that, and then the truck drives off as soon as it's full, and then you have another truck in line right when you need it. Something like that would be a little more efficient than having to fill up drums and then ship them in drums. Anyway, those are a couple of things that I thought of. So that is it for problem number 4.36. Thank you for joining me. Don't forget to like and subscribe, and look forward to making the next video and hope to see you there.